Good morning, students. Today we're going to go over our vocabulary list for Exam 1. Now, one of the pieces of advice I like to give to students, with vocabulary especially, is that you should be able to define each of these terms in your own words. So not the words that I give you, and not the words that you find in a textbook, but you should be able to describe it in such a way that you can explain it to a friend, to a colleague, or even to somebody who doesn't do any programming at all. And when you can do that, that is a pretty good sign that you actually really understand the meaning of the word and can use it effectively and properly. So that's what I want you guys to shoot for as you're looking at these exam words. Get to the point where you can describe them in your own words, and that's what I want to see on the actual exam. I want you to actually describe to me how you understand that word. And as long as that is in line with the meaning, with what I'm actually looking for, you're going to get full points. I'm not going to be terribly worried about grammar or spelling or any of those things. I'm really looking for an understanding. That's what's critical for this particular course. So let's go through them. So the first word we have is structured programming. And structured programming comes from the early days of programming when we started moving away from the go-to statement. So all structured programming actually means is a programming paradigm where we don't use go-to statements. Instead, we use control flow structures and we use looping structures. So if statements, if else, switch statements, while loops, for loops, do while loops, all of these are essentially core ideas in structured programming. So that's really all structured programming means, and I know for most of you that's the only kind of programming you've ever learned. But if we roll back the history belt way back to the beginning of computer programming, we didn't have all of those concepts that gave us structure to how program flow moved through a program. It was all based on go-to statements, which really allowed us to potentially make some really big tripping points for ourselves. So structured programming was really intended to help solve some of the immense flexibility and perhaps too much flexibility that we got from using the go-to statement. Next, we have encapsulation. So that just basically means to contain something. And as computer scientists, we think of encapsulation in terms of encapsulating behavior, encapsulating state. So a function is an example of encapsulating a sequence of commands that we want to be carried out. A data type is encapsulating data in some form. A compound data type, like the structs that we create in C# is encapsulating more than one kind of data into a single structure. And of course, in object-oriented programming, classes define encapsulated state and behavior. They're our way of creating objects which encapsulate and contain these different ideas. And that encapsulation, especially in object-oriented programming, is very much influenced by the things we see in biology, especially cells. Alan Kay and some of the other creators of the original object-oriented programming languages like Smalltalk really were heavily inspired by biology, and were looking at cells as a way of thinking about and organizing programs. State. So in computer science, state just means the current state of the program or of an object in the program, and what that really means is the current value or the values at a particular point in time. So the state of the program is the values of all the variables at that particular point in time. And we can expand that to objects. An object state is just the state of all the variables contained within that object, or all the fields if we're talking C#, inside that object. Behavior is how the object would actually function. So functions are one way of encapsulating behavior, but in classes we also encapsulate behavior with the methods that are invoked and called from within the class. So behavior basically just describes how the program alters and changes data. A class defines the structure of an object and the methods that can be invoked on that object, so what messages it will actually allow to be received. And we often talk about a class as encapsulating state and behavior in one object, and A class can, of course, also be instantiated as an object. So every time we create an object from a class, we're creating a new instance of that class. Those are some of the terms that we use to describe that process. Polymorphism means literally many forms. And primarily in object-oriented programming, we look at the use of interfaces and we look at the use of inheritance. So being able to treat object as one of several potential types. So there's always the actual type of the object, so whatever we call the constructor, whatever class we constructed it from, but it may also have the type of any interfaces it implements and the type of any class it inherits from, or any classes down that inheritance chain, which can actually be as deep as we want to take it. Now, it's not a great idea to go too deep with that because it makes it very hard to understand what that program is doing, but we can certainly do that. Type just refers to the identity of a structure in memory. So type includes things like value types like integers and floats and doubles, and it describes how we're going to store it in memory and what it's actually representing. But also, classes are types in an object-oriented programming language. And compound data types like a struct are also a type. And the difference between a value type and a reference type is a value type stores its data at its particular location it's been assigned in memory. A reference type actually stores an address to another spot in memory where that object actually resides. So all of our objects in C# are reference types. Structs, and then integers, booleans, floats, doubles, shorts, longs, characters, those are all value types in C#. So keep those in mind. You don't necessarily need to know those for the vocabulary purposes, but that's really just good to understand about the C# language. Type checking is basically a process usually done while we're compiling, though it can actually be done separately, where we look at all the declared types in the program, the types of all the variables declared in the program, and we make sure that at no point are we trying to treat something as a type that it is not. So that means if we've declared it as an int, we better be using it as an int all the way through. Now, that also includes things that can be cast. So in C#, if it can be cast implicitly, then we can actually change its type with an implicit cast, and the type checker will be okay with that. If it's an explicit cast, it's possible with an explicit cast, we have to explicitly do that cast. We have to say we are casting this to this other type. So type checking is pretty much a staple of statically typed programming languages like C#, Java, and C and C++. It is not something that we see in a dynamic programming language. That's actually one of the big things that makes a difference between them. So JavaScript or Python or Ruby, which are dynamically typed languages, do not have static type checking. We can also sidestep that in C# programs by using the dynamic keyword, which declares a variable whose type we will not infer until runtime. So that's what type checking is. Casting just means changing a encapsulated value or a type from one type to another type. And some of these casts can happen automatically, which we call implicit casting, like when you assign an integer value to a double. Most programming languages will allow that unless they are very strictly type checked. For example, Kotlin, which runs on the Java virtual machine and is one of the programming languages that you can program Android in, is strongly statically typed. So if you were to use an integer in a double, so assign an integer value to a double, you would have to explicitly cast that. It will not allow it to automatically happen. That is one of the tenets of a strongly statically typed language, is that anytime you're changing a type, you have to explicitly cast. So that is a bit of a difference from C#. Then we also have inheritance. Inheritance is the idea that we inherit part of the structure and behavior of a class from another class. So we set up these ancestry trees where we represent some kind of hierarchical relationship. In UML, we call it generalization. We look for shared attributes and behaviors between some classes. We pull those out of those classes into a generalized base class that those all inherit from and get those state behaviors from. Okay, then we're getting into specific C# terminology, and on the exam I will tell you when we're talking about things in a more theoretical side and when we actually really want to drill down to how it applies in C#. So those are separate sections of the exam. So field in C# is a variable that belongs to a class. That's really what it is, and it can be any type of variable. It can be a value type, it can be a reference type, but it actually is held by the class and is part of that class's state. A method is a function that belongs to a class, and it is representing a message that that class can receive and process. And then we have properties in C#. In C#, properties are actually fields that behave and look or are used as though they were methods. So a property is just a getter and or a setter that sometimes is hooked up to a private backing field, though it doesn't have to be. Sometimes it just computes a value and returns it. But it is actually a method, but we use it like a field with the dot notation and without the parentheses around the name. So we can actually assign it a value if it has a setter, and we can retrieve and use its value if it has a getter. And it doesn't have to have both of those. It can have just one. Then we have our access modifier keywords. So public means that the class is accessible or the method or property is accessible by all code in the program. Protected means that the value or method, so the field, property, or method, is accessible by that class and any class that derives from that class. So it's not available to the rest of the program, but it is available to that class and to classes that inherit from that class. And then we have private, which is not accessible outside of the class, even for a derived class. So that is the most restrictive. Public is the least restrictive, and protected falls between those. And those are all about preventing access. So that means you cannot read that value and you cannot write to that value. If it was a field, if it's a method or a property, it means you cannot invoke that field, or sorry, that method, or run, again, set that property or get from that property. So that's the difference on those. The static modifier in C# when applied to a class means that there is only that instance of the class, or there are no instances, there's only the class definition. And that means we can't instantiate the class, we can just use it directly. A good example is the math class is a static class, so we can access its methods with capital M-A-T-H, math, the name of the class, dot, and then the name of the method. Or any variables declared in it that are static and public, like pi, we can access directly from math.pi as well. The static applied to a field means that there is only one field which is shared by all instances of that class. So we can declare static on a field inside a non-static class, and that means that all of the classes, when we instantiate them and we use that value is shared amongst all of them. So if one of them changes, it's changed for all the instances. So all the objects use the same specific variable if it is a static variable. And if it's a static method, that means that the method belongs to the class definition and not to the instances. So we can also do that just like we talked about with math has, for example, tangent. Well, we can declare a method directly on the class, even if it's a class we normally instantiate. By making that method static, it means it exists at the class level, and we invoke it by saying the class name dot and then the method name. Implicit casting just means a cast that we can do that cannot go wrong. So for example, if we're casting an integer to a Boolean, that's an implicit cast, or sorry, not to a Boolean, an integer to a double, that's an implicit cast because it will always work. There's nothing that can go wrong with that. On the other hand, going the opposite direction is what we call an explicit cast. That's a cast where either some degree of precision may be lost or some kind of error might be thrown. And in that case, we have to explicitly apply the casting operator by surrounding in parentheses the type that we're casting the variable to, and then the variable immediately after those parentheses. To say, for example, if we want to cast a double to an integer, we'd have to put double in parentheses and then the variable name that is the integer. And the reason we have to explicitly cast that is when we convert from a double to an integer, we are throwing away the decimal or the fractional part, which in some cases does not mean we're losing any precision, especially if it's 0.0, then we don't lose anything. But if it's 0.01 or 0.08 or 0.952, any of those, we're actually truncating and throwing away that partial part of the value. So we have to do an explicit cast if we're trying to do that. An interface is, in C#, a way of defining methods that a class must implement if it implements the interface. So the interface serves as another possible type that we can treat that class as, and we can treat disparate classes that all inherit or use the same interface as being the same type. And that's really the power of interfaces. It allows us to provide a number of methods that we know anything implementing that interface will have, and we can use it over and over again. One that you've been working with a lot is the IEnumerable interface. List implements it, Stack implements it, Quay implements it. All of these collections that you've dealt with in the past all implement the IEnumerable interface. And what the IEnumerable interface actually says is that you can get an enumerator. In other words, you can put this in a for loop or a for each loop, and it's going to work regardless of what kind of data type or what kind of data structure it is. Because it implements that IEnumerable interface, you know that you can enumerate it. You can get the specific values back out of it. You can iterate over them, or you can access them using the bracket notation. Virtual is part of how C# does inheritance. So a virtual method is one that can be overridden, so can be replaced in a derived class, but it doesn't have to be. It actually has a body defined, and you have the option of replacing it. If it's declared abstract, that means that it can also be overridden in a base class, but there is no body, or sorry, a derived class, but there is no body to it. So we have to override it if we're going to use it. So it has no body, it has to be overridden. Virtual has a body, has the option of being overridden, and then if it's just a method with no virtual or abstract, then it cannot be overridden. It has to be one of those in order for it to be overridden. We can also apply the sealed to any already overridden method. So that basically says this cannot be overridden any further. We can't use sealed unless the method we're sealing has already been overridden once, because it doesn't make sense to do it on a method that's never been overridden, because if that method was not declared originally abstract or virtual, it cannot be overridden to begin with. So that's virtual abstract. Override just means that you are replacing the definition from the base class of a method with the new method. So that basically is how we can replace the functionality of a virtual or supply the functionality of an abstract method in a derived class. And sealed means we can't derive that any farther. Now that's for when we're dealing with methods or fields. When we're dealing with classes, they have a slightly different meaning. Virtual cannot be applied to a class. You can't have a virtual class. Abstract declared on a class means that that class is intended to be used only as a base class. We can't instantiate it by itself. So it will not be able to be constructed. And abstract classes can contain abstract methods. They're the only kind of class that can, because if it can be instantiated, i.e. it's not abstract, you should be able to invoke all the methods on that class. And an abstract method cannot be invoked directly. It has to be derived in order to be invoked, because remember, an abstract method has no body. So an abstract class will always is the only kind of class that contains abstract methods. Now, it can also contain regular methods or virtual methods and have actual implementations for those. It doesn't have to only contain abstract methods, but it is the only kind that can contain an abstract method. Override doesn't really apply to classes. If we want to derive a class, we actually say it inherits from that class, and that's the override mechanism applied at the class level. And we can also seal classes. The sealed keyword applied to a class means that that class cannot be inherited from. You can have a descendant class that derives from it. It is not usable as a base class. Finally, we have the as and is casting operators. These only work with reference types, so you can't use them with a value type, i.e. you can't say an integer is a double or vice versa. It only works with reference types. But what they do is the as casting operator allows you to do casting. You can say, for example, if I have class A and I want to cast it to be class B, so I take the variable that is class A and I say as and then class B, and it will try to cast it to be class B. If that cast is possible, it just happens, and that's the data type that we are now treating that variable A as an instance of class B. If it fails, it evaluates to null, and that's different than the explicit casting operator with the parentheses around the type. If we apply the explicit casting operator to a cast that cannot be done, it throws a exception. An invalid cast exception is the exception it will throw. So as does not throw exceptions, but it can only be used with reference types. And the is keyword is also a casting operator, but it tests to see if the cast is possible. So we say if variable A is of class B, that will give us a Boolean result, which will be true if the cast is possible, false if it is not. So those are a couple of casting operators that we end up using a lot, and we'll use them a lot for a little further down the line in this class as we start seeing, especially in GUI design with Windows Presentation Foundation, we start using a data context. That's going to come into play. All right. So those are all the vocabulary words that I want you to be familiar with for Exam 1. So take the time, write down your own definition for each of those. Should be a couple sentences probably for each one, just describing how you think about it, and maybe bounce those definitions off of friends, see what they think, see if they agree with you or don't agree with you. That's a good way of kind of really zeroing in on your own understanding of those terms. And that's a good way of helping you build that model of how the computer actually works in your own reasoning about the computer, that notional machine we talked about at the beginning of the semester, which is an important part of developing your own knowledge and understanding as a programmer to come up with your way of describing all of these kinds of ideas. All right, that is it for the vocab. Stay healthy.